radiant energy transmitted to the Earth from the Sun and the energy that is absorbed by the Earth and then re-radiated out to space through the atmosphere comprise solar and terrestrial radiation. They are primary factors in the study of meteorological phenomena. However, to aid our understanding of this interplay of solar energy, it is necessary to travel back into time 400 years to trace the history of radiant energy as a physical concept. Light, for instance, is a form of energy with which scientists have always been vitally concerned. Sir Isaac Newton, 17th century physicist, was a strong advocate of the theory that luminous bodies, such as the sun, shoot off tiny particles which travel at high speeds in straight lines like bullets from a gun. These were called corpuscles, and the concept became known as the corpuscular theory of light. It explained the simple factors of reflection and refraction and other light properties as they were known at the time. However, as scientific knowledge grew, the corpuscular theory proved inadequate when physicists attempted interpretation of such phenomena as diffraction and interference. The wave theory of light then came into more general acceptance, with Fresnel and other 18th century French physicists visualizing light as traveling in waves, similar to ripples on disturbed water. Another early problem was speed of light propagation, determined to be approximately 186,000 miles per second. 19th century physicists, experimenting with light and electricity, concluded that these phenomena were simply different forms of the same type of electromagnetic wave. Subsequent work with ultraviolet, cosmic, infrared, and radio waves verified the conclusion that all these types of wave energy were electromagnetic waves of varying form. Significant differences were found only in frequency and wavelength. The length of a wave is the distance between two adjacent crests or pulses. Frequency is the number of waves passing a fixed point per second. We know that heat is simply a form of energy due to molecular vibration of a specific substance. There are three methods by which heat may be transferred. First, conduction, the transfer of heat from one portion of a medium to another portion of the same medium without visible motion of the medium itself. Second, convection, the transfer of heat by bodily movement of the substance containing heat. And third, radiation, the transfer of heat without depending on the intervening medium. When a light bulb's filament is heated by electric current, we see a certain amount of the filament's radiation as light. However, other radiation from the bulb is felt as heat, despite the fact that the bulb is largely evacuated. That could be caused only by radiation, since a partial vacuum and a layer of poor conducting air intervene.
Here is a typical 12-story office building with diversified tenancy. Let's study the elevator traffic during a typical day and see what such an automatic control must do. First comes the morning rush. Everyone wants to go up, and there's little or no down travel. After that short concentrated rush period, traffic is almost even up and down for most of the morning. Just before the lunch hour, there's a surge of down traffic. And right after the lunch hour, the pattern is reversed. A heavier upsurge, but still considerable down traffic. For most of the afternoon, it's about even up and down, until late afternoon when everyone wants to go down in a few minutes period. So we have these distinct traffic flow patterns. Up peak, balanced up-down, heavier down, heavier up, and down peak. And of course, during evening hours and holidays, we need night service. An adequate supervisory control must first of all provide for all 6 types of building traffic. Second, it should be flexible and prevent the bunching of cars due to sudden changes in the traffic pattern. And third, it should be automatic, so elevator supervisors can do their important public relations work as information center and first official representatives of the building. For over 25 years, Otis engineers have been developing features that provide better group control. Peak period control, introduced by Otis in 1937, was the first system to coordinate many features so that they were automatically at the disposal of the supervisor. Then, in recent years, Otis has brought another revolutionary advance, the application of electronics. Electronics have brought such magic into our lives as television and radar, and have helped industry do countless things quicker and better and at lower cost. Otis brought the magic touch of modern electronics to elevatoring by harnessing the precise, instant speed of light accuracy of the electronic tube to signal control. Up in the penthouse, the electronic controller, a marvel of electronic engineering, precise, instant, accurate in its control. But to really understand what goes on here, let's think of this little fellow as the brain of autotronic elevatoring, as the little guy who isn't there, if you look for him, but who is always on the job, following through during each traffic period of the day. Let's see how he does it. It's early morning, and soon everybody will be coming to work. We want to take people up to their floors quickly, and then we want to return the cars to the main floor as rapidly as possible for more passengers. All the supervisor has to do is turn the traffic flow dial to up, and our autotronic brain takes over, putting the up peak program into immediate action. During the up peak program, cars are dispatched at timed intervals from the lower terminal only. They are not dispatched at any set sequence, but the first available car always gets the signal. Otis non-sequence dispatching means shorter waits and increased traffic handling capacity because cars are kept moving. A car that has made a fast trip is never held up to wait for a slow car. There's the signal for this car, so up we go. Taking passengers to their floors. By the 9th floor, our car is empty. This is the highest call. There is no one waiting above, and we want the car back at the main floor as quickly as possible. So when the car stops, our autotronic brain is ready to give an immediate down signal. And the car automatically reverses.
Right now, this hollow billet is a thick-walled tube, somewhat rough on its surface, but absolutely seamless. Truly walls without welds, hurrying on to do service in a towering skyscraper or in a deep oil or gas well. This piercing operation is a rough, tough test of the steel in the tube. Only the finest steel, properly heated, can withstand the punishment it takes here. Let's look behind the scenes of this powerful machine and see what actually takes place inside. The pass is a combination of two power-driven barrel-shaped rolls. This is the piercing point, and it is supported on the forward end by a thrust bar. The bar is free to rotate, but cannot move back and forth in a line. Here comes a heated billet to be pierced. The piercer point makes its first contact with the heated billet at the center hole. When the billet is pushed into the piercing mill, the rolls take hold of it and advance it and rotate it over the piercer point. The powerful pulling and rotating action of the mill causes the metal to flow over the piercer point, with the result that the pierced round slides over the bar like a sleeve over your arm. This combined action of the rolls and piercer point form the hole in the center and throughout the length of the billet. The pierced shell, still at a soft forging temperature, is now ready for its run through the continuous mill, the first continuous seamless pipe mill in the world. From this point on, all operations are entirely automatic. First, a long cylindrical bar or mandrel is inserted into the shell. The bar or mandrel is not fixed as in the piercing mill.
It moves forward with the shell around it into the continuous mill. This operation is called rolling on a bar. This part of the continuous mill is called the mandrel mill. It has 9 pairs of semicircular grooved rolls so arranged at right angles to each other that the rolls alternately engage one side, then the other of the shell's outer surface. Reduction of the shell's diameter over the mandrel is the first step. The first 2 sets of roll stands do that. The next 4 sets of rolls reduce the wall thickness. The next 2 polish and perfect the surface of the shell. And the last, or 9th stand, rounds up the shell and loosens it from the mandrel. After passing through the mandrel mill, the shell and mandrel are conveyed to a mandrel bar stripper,